All right, welcome back. Today we've got a guest speaker, Jim Tansy. He's a previous nuclear engineering department supervisor here at Energy Northwest. He's got a master's degree in material science. And right now he's an operations instructor teaching the ILC class through our 21-month-long program to get a license to operate a reactor. We're going to talk about what saturation is, phases of materials. Specifically, we're going to focus on water because that's what we deal with in our nuclear power plant, right? We boil water to make steam to spin the generator, the turbine. We don't spin the generator, we spin the turbine to spin the generator to make the money. This will be an interview style thing. Welcome, Jim.
All right, thanks for having me.
So one of the confusing things that students often have problems with is the word saturation. When you hear the word saturation, it often invokes ideas of something that's wet or something that's saturated, right? It's all soggy, it's damp. But saturation for us means a little something different. Can you talk through what saturation means for us?
Yeah, sure. So using that analogy, right, you've got everybody can kind of relate to, say, a sponge, and you're soaking up water, and at a certain point, when the sponge is saturated, it can't suck up any more water, right? It'll just start dripping out.
Yeah, that makes sense.
So if you think of it in terms of water, and in particular steam, which is what we want to make in a reactor, water itself has a certain amount of heat that can be added to it to a point where now there is so much heat in that particular state. Let's say we start off with liquid water. You can heat that water up. You get a certain amount of heat to a point where when you reach saturation, now something else has to change, right? The temperature of that liquid can't go up anymore. It has to change state.
So the molecules in its liquid state have absorbed all the excitation, all the energy that it can, and it can just simply no longer stay liquid in its entirety.
That's correct.
Okay.
So when you reach the point where so much heat is now in that system, you will now have to change state, or change phase.
Okay.
So in this case, right, if you get to the saturation conditions and you continue to add heat into that system, now that liquid is going to start turning into vapor, into steam.
Okay. So when I was adding heat up to that saturation point, the temperature of the water, the liquid, was changing, right? I was went from 100 degrees Fahrenheit to 200 degrees Fahrenheit to presumably our saturation temperature of 212 degrees Fahrenheit at room, standard atmospheric pressure. What's happening with temperature now as I continue to add heat?
So now, right, so let's get back a little bit to first principles. So as you alluded to, right, as you add heat to, say, the liquid water, the liquid molecules are moving around and they're spacing each other out, but they're still staying liquid. To now break away and turn into a steam bubble, right, that's going to take energy. And so once you hit the saturation conditions, all the heat that's now added into that system at that temperature and pressure is being used to convert the liquid into the gas, into the steam. And so what you basically have is, if you hold, let's say, the pressure of the system constant, since the heat coming in is all being used to convert the liquid into steam or into gas, the temperature will also stay constant until until all of that liquid is converted into steam. So that process, we call the heat involved there, called latent heat of vaporization, right? All that heat that's being put in, that's all happening at a constant pressure, constant temperature, until all the liquid has been transformed into steam.
I like that you brought up the word latent. So we have two types of heat that we're dealing with here. And when we were talking about bringing the temperature up to the saturation point, up to 212 degrees Fahrenheit, we were adding sensible heat. Mm-hmm. So at the saturation point, you're saying that now we're no longer adding sensible heat. We're adding latent heat. And I think it's the same heat, right? The heat was sensible heat, and now we're calling it latent heat, but the reason it's latent heat is because it's not driving a temperature change, it's just adding energy to the molecules and turning it into steam.
That's right. So that's why if you look at a graph of temperature for a constant pressure, you'll see that the temperature stays flat during that transformation in phase from liquid to gas.
Do you mind showing us?
Yeah, sure. So if we were to plot, let's say, temperature here, and we'll talk about specific volume, I guess we can do that. And so again, we'll talk about keeping, in this case, pressure constant. And if we were to plot what the temperature versus the specific volume was for a constant pressure, you're going to see so for some given pressure, right? So I keep the pressure constant. This is a isobar, right? And we're talking about water. So for a given mass of water at a certain temperature.
This could be, when you say that, this could be a 2-gallon or 5-gallon bucket, or this could be a 100,000-gallon tank, right?
That's right. So when we use specific volume, it's, we'll take the actual volume divided by the mass. So now it's, it's what we call specific volume. And so it's a intensive property that basically, right, it's based on the mass of the system, not how much it may expand or contract.
Nice.
Okay. So for a given pressure, let's just say we're, do you use US units or metric?
We use US units.
Okay.
Yep.
Let's just say we're at 1 atmosphere. Just standard pressure, what we feel every day here on the Earth. We know that for water, right? So we got a water system here. Let's say I'm starting here, I don't know, at 40 degrees Fahrenheit, right? And
Okay.
I'll have some specific volume. And then as I add heat to the system, what I'm going to see is temperature will go up, specific volume will start to increase as well, right? Because the molecules are moving around in the liquid, and they're starting to, for the same mass, they're going to take up a little bit larger
Because
volume.
it's cubic feet per pound mass, and the cubic feet, the volume is
The
going
amount
up.
of volume that same amount of mass will encompass is going to go up.
That's based on Charles' law, Boyle's law.
Boyle's or Charles.
One of the two. Charles Boyle.
Right. And then I'll get up to a number that should be recognizable to all of us. I'll get up to 212 degrees Fahrenheit. And I'll hit the first spot here on our temperature specific volume diagram, right? So at this point, at 212, we all know that that's the boiling point of water at 1 atmosphere. This is what we call the saturation temperature for this pressure. So at this point, right now, if I continue to add heat, I'm going to follow along this line right here. So you'll see that this is now constant temperature, but my volume of my system is going to continue to get bigger. So what's happening here is I'm boiling, right? So now steam bubbles are being generated. And so when you're underneath this part of the diagram, you're now looking at a mixture of liquid and vapor. Outside the dome here, this would be all liquid water, right? Because I haven't reached the boiling point.
Okay.
Underneath here, now I have a combination of liquid at 212 and vapor or steam at 212 degrees.
And it's a mixture, and whatever percentage of that, like in the middle of that line, would be half and half, presumably.
Right. So throughout this whole process, if I continue on, I keep adding heat and making more and more of the liquids turning into steam, I'll get over to this point here where now all the liquid has been converted into steam.
Okay.
But again, it's still at the constant temperature. So any point along here, right, it's just a matter of adding more heat to drive that phase change between liquid to gas, liquid to vapor.
Interesting. And
And then once I get to full steam, if I continue to add more heat at a constant pressure, well, now I'm going to start to superheat.
it then becomes sensible heat again.
That's right. Now I'm raising, as you'll see, right? So now if I add more heat, now my temperature is going to start to creep up, as well as mixture itself is going to
Okay.
continue to expand.
So that horizontal line inside that saturation curve, that is, there's a quality associated with that steam water mixture, what we call a two-phase fluid, right?
Mhm.
It's both steam and water, steam and liquid, gas and liquid, vapor and liquid. And the closer we get to the right side of that saturation curve, the more steam is present and less water, which means it's a higher quality.
That's right.
Okay. And then, but when we first start off, so this is not an instantaneous process. There actually takes a lot of energy to do that phase change.
That's right.
So if I had something that was, say, 75% water, and it was frozen, and I had to start slapping it to add energy to it, right?
Like a frozen chicken?
Like a frozen chicken, great example. I would have to deal with not only the 40 degrees Fahrenheit to the 212 degrees Fahrenheit to the whatever the cooking temperature I want is, right? Or the cooked temperature, but there's actually more energy added during that phase change than the sensible heat added on either end of the saturation curve, is what it looks like to me.
Yeah. Yeah, so all along the way, right, this is taking larger and larger amounts of heat. It's just when you change phases, when you go from liquid to steam in this case, it takes a large amount of heat to do that for a given saturation temperature and pressure. Obviously, you could see that, let's say I put this in, I don't know, like pressure cooker or something where I increase the pressure of the system, right?
Okay.
Now you could,
An Instapot, yeah.
different color, but you would have now a new isobar, right?
Yep.
And so at a higher pressure at P1 greater than P0, I don't know, maybe it's 2 atmospheres.
Okay.
Whatever the value is, something higher, right? Well,
Yeah.
now my corresponding saturation temperature is going to be much higher. However, if you think of the amount of heat required for the phase change, it's really, think of it as the area underneath the curve, underneath the isopar.
Okay.
By raising that pressure, right, you can, it takes less energy, so to speak, to get from this point to this point. The length of that
Interesting.
line is going to shorten. Lower pressures, obviously, it's going to take larger amounts.
That's a great idea for a future discussion for another class, because this is describing why an Instapot works the way it does. How can you cook a chicken in an hour in the oven, but you can cook it in 10 minutes in an Instapot?
Mhm.
And it has to do with raising the pressure, reduces the amount of energy needed to be added.
That's right. All right, so.
So that whole blue, if you could retrace that curve,
This first one?
the actual big saturation curve. Just trace over that saturation curve.
So
It has two sides, yeah.
this one here.
So all along there is saturation. So what you're saying is as I raise pressure, I am reducing the amount of energy needed to do that phase change all the way up to, but it stops at some point.
This point here.
Yeah.
Yeah, so on this side of our saturation curve is where we're going to have liquid.
Okay.
And on this side, right, we're going to have vapor.
And everything under the curve is,
And
of course, the two
anything under
phase.
the curve is a combination of liquid and vapor.
What happens up at that top point?
So the top point, we call that the critical point.
Okay.
You may see that in the literature. And essentially, if you were to have pressure of the system set up so that it came and it just touched that point and head up, effectively what you're looking at is not really a phase change at this point. You wouldn't really be able to differentiate between the fluid that would look like liquid versus vapor. It would
It
just
kind
be
of
a
exists
single fluid.
Is both
state.
at that point.
That's right.
Okay.
It's not really, I mean, it's nice from a scientific perspective, I guess, what's going on here for as far as practical application in some system or some machine. It's not really useful.
It's beyond something we would need to worry about.
That's right.
Okay.
But it's very hard to distinguish, you know, between the liquid and the vapor phase once you hit this critical point. Where most machines work is going to be, that uses steam, is going to be somewhere underneath this.
And it depends on the substance we're talking about. For example, carbon dioxide, it does play a different kind of role, right? Because we live, we're at atmospheric pressure with carbon dioxide, we're transitioning straight from a solid to a gas because the solid just evaporates. And we never go from solid to liquid to gas like we do with water.
Right. Because
its critical point, its curve just looks entirely different and needs a whole different set of pressures.
Right.
Interesting, right?
I'm here to help people understand, right, what's going on here. So again, just to recap, right, for a liquid water system, for a fixed pressure, say, for some given pressure, if we were to plot what the temperature did as a function of the specific volume, we would get this saturation curve. So we could add heat to the system as long as it was still in the liquid state. You may see a term called subcooled liquid. Just means it's at a temperature below the saturation temperature.
Well, I'm glad you said that because that's often confusing too, right, for students, because subcooled invokes ideas, other visual ideas that...
So subcooled, I mean, in the simplest form, just think of it as if I know what my saturation temperature is, where I'm going to start transforming liquid into vapor.
For whatever given pressure.
However much I'm below that temperature for a given pressure, that amount of delta, if you will, it's actually the amount of heat I'm missing. But
okay.
For simplistic terms, you know, for a visual, how far away I am from that point is the amount of what we call subcooling that you would have in that system.
So the subcooling is, another way of saying that, is the amount of sensible heat that needs to be added at that given pressure to get to the saturation point.
That's right.
Okay.
And it's important in a boiling water reactor because when the water is coming into the reactor to be warmed up, right? You have the reactor fissioning, creating heat. You want to make sure that the water coming into the reactor stays in the liquid state until you get up through a portion of the fuel assemblies themselves and have the boiling occur there. You don't want the water to start boiling soon after it gets in the reactor. You want to have it routed through and get up and through into the fuel region before it actually hits this saturation point and starts turning into steam.
Yeah, that's a good review point for many of these students, because if we do start boiling lower down on the fuel channel, that boiling, all those bubbles collate in the center of the fuel channel, and eventually you have more and more and more until it reaches the fuel channel walls, and now we have a dry out condition.
That's right.
And we've basically exposed fuel to steam, and the steam doesn't remove as much heat as liquid does.
That's right.
Excellent.
So you'll start off here subcooled, so to speak, for a given pressure, and then when you hit the corresponding saturation temperature for water at standard conditions, that's going to be 212 degrees. For higher pressures, it's going to be higher, right? If I was at a higher pressure here, my saturation temperature would be something above standard.
Okay.
In a reactor, we're typically looking, this number here would correspond somewhere around 548 to 550 degrees. We're also operating at 1,035 pounds.
And if we were to use our steam tables to find that, if we knew the pressure, if we knew that our pressure reactor was at 1,000 psi then we could look up the steam tables and see what that corresponding saturation temperature was.
Right.
That's where the value of the steam tables comes in for us.
Yeah. So once you hit that, now as you continue to add heat, you go through that phase change. All the liquid underneath the dome here now is you're converting the liquid into steam until you've converted it all over to here.
Okay.
For that pressure. And any mixture in between here will correspond to a certain what we call steam quality. Steam quality just being, what mass of the system is steam divided by the total mass of the system, which would be the mass of the liquid plus the mass of the steam.
Okay, so which is why 100% quality would be that the right side of that saturation curve,
That's right.
because of 100% of that mass is now steam.
Now steam, that's right. And that's the quality of steam we're looking for to exit the reactor and then drive the main turbine and then eventually the generator. So, and you're looking for highest quality steam you can get as close to 100% as you can get.
Okay. Any other specific things you wanted to bring up or talk about?
Well, I guess one other, we talk a lot about solids, or talk about liquid and gas, realize too, right? You can also have solid state. Again, if we want to talk about water, right, we call that ice. So the same type of phenomenon will happen. Let's say looking at a different phase diagram for water. If you wanted to change phase from solid to liquid, right, that's going to be, if you start off with really cold ice and you start heating it up, the ice will get warmer but stay solid, and then you'll hit that point called latent heat infusion.
Okay.
All right, not to be confused with vaporization, but again, once the solid starts turning to liquid, all the heat you're adding is feeding that phase change, so that temperature corresponding to that phase change is going to be constant for a given pressure. So it's the same principles involved.
In fact, that's more applicable to the chicken, going from frozen to thawed, and we wouldn't use this liquid to vapor as chicken unless we were trying to steam it from the inside out.
The idea being, though, right, if you're gonna change from one phase to another, for that corresponding temperature that's going to occur at, it's going to be constant through that phase change.
Okay,
Just like we have here with the liquid and vapor.
I like it.
Saturated temperature and pressure, we talked about that.
We hit a lot of this. Phase
Talked
diagram.
about phase change.
Do you want to do one on the enthalpy? PV and U?
Could. Yeah, we could tag on right onto this.
Yeah. What I'll do